Good afternoon, everyone. It's my pleasure to welcome you here today on behalf of the Civil, Environmental, and Geodetic Engineering Department. I'm the chair of the department, Allison McKay, and every spring we have the opportunity to come together and really think about the legacy that THB left in terms of his contributions to the field of geotechnical engineering. And we do that by bringing in a distinguished lecturer, Dr. Brady, who will be here with us today, and also inviting you, our current students, past alumni, local industry collaborators, and friends of the department to come together. And so today in our program, we'll be able to give you a little bit of highlight of all of the innovation that's been growing in the geotechnical engineering subdisciplinary area within our department. So some of this got really kicked off 4 or 5 years ago when we upgraded our lab facilities and really focusing on both regional and national and international needs where geotechnical engineering can be offering solutions. So it's my pleasure to introduce our MC, apologies, Professor Min Liu, who is an assistant professor in our department, who's part of the growing geotechnical group here.
Hello everyone, my name is Min Liu. It's good to see you all here. I know that a lot of you know PH Wu in person, but some of you, I know that there are new faces here, some students that just joined Ohio State, but doesn't really know who PH Wu is. So let me welcome Professor Geodetic to talk more about PH. Go ahead.
Thank you.
Thank you.
Can you hear me better now? Yes? Good. Okay, wrong microphone. All right? Oh, yeah, much better. Okay, so before I start, I wanted to let you know that we've received a philanthropic donation, and I think here we are, that was generally donated to the Geotechnical group, or also the Department of Civil Engineering in general. We'll hear a lot more about this next year. Right now, we've been asked to keep some of the details anonymous. And this endowment will mainly fund scholarships for students interested in pursuing a career in geotechnical engineering, but also support geotechnical research, provide faculty and graduate student support, and assist in supporting travel for graduate students to present research finding at conferences. We're very lucky to have received this endowment, and more news will be published in the next year. All right, let me close this. I'd like to tell you a little bit about T.H. Wu. In my opinion, he was not only brilliant, but a very unconventional pioneer. Some of the areas like georisk, the reinforcement of slopes with root systems, so what we typically call biotechnical stabilization of slopes, the area of glaciology. He was doing things when in areas that nobody was touching at the time. He's been honored and even had conferences follow up his work, like the conference in Taipei a few years ago. He was extremely curious. He came to our department even in his 90s, and I was very lucky to be maybe his last postdoc, because through the years he would give me assignments, papers to read, but also he was incredibly interested. Here's a picture with Von Griffith and at a local Geo Institute talk here in Ohio. I learned how much he was, whenever he had his what he called projects, he would take them to a level that was of perfection, that was really amazing. I remember with Bob Holt, when he was here, who loves opera, he brought in some CDs for him, showing how he had made some recordings of his playing of piano, and he played absolutely beautifully at, I would say, the professional level, or near the professional level. But many people didn't know about this because he was extremely humble too. So through the years that I was lucky to be having lunches and meeting with him on a regular basis, he came usually 1 to 2 times per week to the lab. I'm sorry, to the department. We would have discussions. When I would ask him a question, he says, "Well, you haven't read this particular paper." And these are 2 papers that he made me read, and actually he always checked that I had read them, okay, asking me questions. We don't do that to students, but he did that to me. He loved these series of lectures, and he would often be sitting, usually over there where Kevin is today, taking notes, and I remember he would later on meet with me, and we would discuss the wonderful lectures of Jim Mitchell, Ed Kavazanjian, and so on and so forth. For some practicing engineers, or researchers, he was known for geotechnical reliability, and some areas of geotechnical engineering that I really have a tough time even reading the introduction of the papers because they're way beyond my knowledge of mathematics. He also was, for people of my generation, a pioneer in terms of education. When I went to school in the 70s, in the mid 70s, most of the books were really complicated. You almost need to have taken a geotechnical course before you could read an introductory geotechnical book. And his book, Soil Mechanics, was one of those that actually basically brought in, explained the basic concepts extremely well. And so there's a large generation of practicing geotechnical engineers who owe him a great debt for bringing us into the field in an understandable way. Not in the Terzaghi way, if you know what I mean. In certain areas that we don't associate necessarily with traditional geotechnical engineer, he didn't mind stepping outside of his area of comfort and having also great contributions. And there's a whole group of people who have conferences on topics that he brought in forward within civil engineering. He was also, he was born in China. He studied at St. John University in Shanghai. Geotechnical engineering was not the area that he originally wanted to study, but he left China just before the revolution and went to University of Illinois, where he met Terzaghi and then had his advisor as Ralph Peck. He was one of the first students of Ralph Peck. And so he was really, how can I say, he was together with some of the pioneers of geotechnical engineering and published many papers that you can still see quoted extensively today in many areas that are very, very diverse. He loved nature. He had certain periods of the year where you knew that he would not be here at Ohio State because he loved walking. He loved taking long trips. And through these he often, through his hikings, would be looking, sometimes even sharing photos that he had taken on issues like slope erosion, slope stability, soil erosion, and he drew from his love of nature a lot of the things that he later investigated. One of the areas that got him into, for example, biotechnical remediation was looking at some, in the 1950s, some of the effects of deforestation in Alaska, and that brought in the whole area of research and publications into the field of soil-root interaction and biotechnical remediation. He was a professor at Michigan State University before coming here. And he had also some unconventional collaborations during his career. And that took him all over the world, whether it's at NGI, serving for the United Nations as a consultant, for the Punjab Agricultural University in India. He was not afraid of traveling to Antarctica and studying. By the way, when I spoke with him about going to Antarctica in 1967, he flew in one of these propeller planes for hours. It was not easy to get to Antarctica, especially in 1967. He was analyzing ice cores, and that was really the first time he was analyzing ice cores. So he was somebody who was really not afraid of going outside of his area and learn new things. He retired in 1994, and for decades, we were really, really lucky not only to have him in our department, but also to work with students here at Ohio State. And as I said to him, I consider myself one of his last students. Just an anecdote, about 2 or 3 weeks after I had joined Ohio State in 2016, he came to my office and he says, I need a student to help me because I have this slope that is instrumented and it's about 30 feet high, and I need somebody to help me with the instrumentation. So I found a student. She was quite fit. So I said, well, you're going to make sure you carry all the equipment, that you help TH with all the readings, and because, you know, he's 89 years old, so please, you know, take good care of him. She said yes, and then a week later, she came to my office, and she started complaining. He wouldn't let me do anything. You know, he was going up and down the slope, taking all the readings himself. Okay, I wanted to take a reading, he wouldn't let me. Okay, so I told her, don't worry, you were part of the safety crew. Okay, if something would have happened to him, you had your cell phone with you. That was a really, really precious part. But that was TH, a very unconventional and absolutely endearing person. He really loved these THU lectures. The first few years, I would suggest names to him, and we've been very, very lucky because none of the people that we have asked, including Brady, have ever said no to coming here. These are some of the pictures from TH with Bob Halls, Ed Kavazanjian, and others, and it's really my privilege to show you a little bit of what TH meant to all of us, and thank you for being here, honoring his legacy, memory, and the many accomplishments he had. Thank you very much.
Thank you, Daniel. That was a fantastic introduction about PhD, and hope a lot of you, although you don't know him personally, get some juice from it. So Patrick and I, the other assistant professor coming into our department this year, we have some news to share. So last year was an exciting year, Patrick, right? We have a new geotechnical lab, research lab that is underway, so it's under construction. Hopefully we'll show you next THU lecture. And then we have 4 new graduate student researchers joining our lab this year, working with Patrick and I on some of the topics. And then we have a lot of funding coming in as well, supporting our students. Last year we have research coming in from ODOT, remote sensing of inventory of higher landslides. And then Patrick received another funding from NSF Rapid, working on site investigation and liquefaction studies for 2023 Turkey earthquakes. And then I myself received a DoD Europe fund to purchase an instrument. It's called Environmental Factor Automated System. It's for research for permafrost and then hydrate studies. So we are really excited that the program is expanded. Yep. And for our courses, we have our Geotechnical Lab courses this year. We expanded that as well, so we are supporting about 140 undergraduate students this year. I really want to thank CDL Engineering Corporation for sponsoring the lab. So it's really nice to our students that they can learn it in a really well setting. So I'll pass it over to Patrick to do the introduction for Mr. Cox.
Thank you, man. All right, so just a brief introduction for Brady. I'm excited to introduce Professor Brady Cox for our 2024 THU Distinguished Lecture. I've personally known Brady since the days I was applying for graduate school several years ago, and we've since collaborated on some research, and Brady has often served as a mentor for me and someone who I look to as a role model, professor, and engineer. I expect there's very few who have sustained the same success as Brady while also retaining a humble and approachable character. Beyond academics, Brady's completed an Ironman triathlon consisting of a 2.4-mile swim, a 112-mile bike ride, and a 26-mile, basically a marathon run. And before meeting Brady, I did not know this was possible. And after a Google search, less than 0.005% of humans have completed this event. So it's really amazing. And to go off of his more professional bio, Dr. Cox is a professor in the Department of Civil and Environmental Engineering at Utah State University. And prior to joining Utah State, he served on the faculty of the University of Texas for 8 years, as well as the University of Arkansas for 6 years. Dr. Cox specializes in geotechnical engineering with emphasis on issues related to seismic design, as well as in situ site characterization for major construction projects and critical nuclear facilities. His research efforts combine experimental field testing and computational analyses for using high-performance computing for subsurface images and multidimensional seismic site response analysis. Dr. Cox is a recipient of the Presidential Early Career Award for Scientists and Engineers, which he actually received in a ceremony at the White House from President Barack Obama. He's authored over 150 peer-reviewed publications and is the director of the recently formed Utah Earthquake Engineering Center, which he told us a little bit about already. Also add that Brady has recently received the Shear Prakash Award by the ACE Geo Institute for his contribution to geotechnical engineering and soil dynamics. And he's going to be presenting a distinguished lecture in Vancouver in a couple weeks now. We're proud to have Brady here with us today.
I'm going to turn, oh, it works. That might take a minute. I'm going to turn that off so we don't get feedback. Thank you, everyone, for being here. I really appreciate the invitation. And I really enjoyed, Daniel, hearing about Professor Wu. I knew about Professor Wu, but I didn't know all of those details. And I really enjoyed learning more and seeing a lot of the pictures. What an incredible career, what an incredible life. How many people in here are former students of Professor Wu? Excellent, great. It's really neat to see people come out and still support this lecture. So thank you for attending. I hope one day that You know, to me, that's the greatest legacy I think that you can leave, is having people who care enough about you to come back and continue supporting you. I'm going to move this screen just a little bit so I can look more directly at you rather than off to the side. Give me just a minute. That'll probably work. I'm so short I can barely see over this. You can see me from here up. I'll stand a little bit to the side. So I'm here today to talk to you about non-invasive subsurface site characterization. If you don't know this trick, write this down, the first thing you write in your notes. Control-Alt-Shift-H. Control-Alt-Shift-H. There we go. You can hide the zoom controls like that. Sounds weird that they would do that, right? Seems pretty convoluted. You got that? Okay. Non-invasive subsurface site characterization. Opportunities, challenges, emerging technologies, and advanced analyses. First of all, I think whenever we think about non-invasive imaging, I think about the medical field. I think about previous experiences I've had going to the doctor, maybe for an X-ray, an MRI, an ultrasound. So I have 4 daughters, and I've been to the doctor with my wife many times, and I've seen them put that thing on there and look inside and be able to tell me, you're having another girl. I've heard that 4 times. Pretty exciting. And, you know, ultrasounds of the past, like this one over here, they were pretty grainy. And now it's incredible. I've even seen advertisements. You can go to a mall, and in a mall, you can have an ultrasound, and they call it 4D. And it's like this picture here that's shown on the right. Okay, so we've made huge advancements in medical imaging over the years. We've had higher resolution imaging. It's spreading out, not just in a doctor's office or a hospital, but even into malls. And so technology is pretty amazing. And then you think about where we're at with subsurface imaging, geotechnical engineering, and a lot of the work that we do is still 1D. Right? We go out, we drill boreholes, we push cones, we create subsurface cross sections sometimes by linking the sticks together and making a 2-dimensional cross section. But that's largely where we're at. We're doing some non-invasive subsurface imaging. And we see these colorful pictures sometimes that people show in reports. Maybe we pay for them, maybe we generate them. And one of the questions that I'm always asked, and sometimes a question that I ask myself, how accurate are these images? And what are they really telling us? And are we just paying for this and putting it in the back of our geotech report? Or is somebody actually using this in the design project? And so, you know, I said, if on an infrastructure project we tell someone they're having a boom, is that what shows up on delivery day? And that's a good question to ask. And are we acknowledging uncertainty, trying to quantify it? So let me give a couple of examples of limitations of traditional subsurface exploration. This is a project that was not too long ago, completed in Austin, Texas. This was a project that I used as a senior level foundation design course where we were designing drilled shafts for this building, the standard in Austin. It was a 17-story above ground and 3-story below ground structure. This is a picture here. It's quite a beautiful building, nicer than any dorms I ever stayed in when I was a student, for sure. But prior to when they started construction, I think in about 2018, it looked like this. The lot looked like this. It was a 4-story parking garage. And so when they performed the geotechnical subsurface investigation for this site, they came in and they drilled 6 borings, which isn't too bad for a lot this size. This is about 300 feet by 200 feet. They couldn't get directly under the area where they wanted to construct the building because the parking garage was there. And at the time, you know, the geotech money, the site characterization money, it's often the first money to get spent on a project. And people don't like to see the money disappearing right away. So they might be a little stingy to start with on that money. So they drilled the boreholes. 6 of them. And if you look at the area of the site, it's about 60,000 square feet. The area of the borings, I was generous and I put in a borehole diameter of half a foot. Okay. That might be what we drill, like a hollow stem auger, but we're sampling if we're running split spoons less than 2 inches in diameter, and if we're pushing Shelby tubes, maybe 3 inches in diameter. So I was generous, I said half a foot. If you calculate the area of the borings then, 6 of those borings, that's 1.2 feet squared. And if you take the ratio, 0.002%, so even less boring explorations than people who complete Ironmans. That was 0.005%.
Yeah, that's what I saw.
I didn't know that, Patrick. So that's a pretty low number. And that's it. I would say that if you said you had 6 borings on a project site this big, you'd be pretty happy. If you talk about in terms of volume, that ratio would go down a lot, okay? Because we're only sampling maybe every 5 feet vertically, so we're not seeing a lot of the subsurface. So if we have a better way to look at more of the subsurface, that would be good. Here's one more example. This one's for the Sam Houston Tollway ship channel bridge replacement. This was from a draft report completed by Fugro. I forgot to mention this was a Terracom project back here, and thanks to them for supporting and sharing this information. So this new bridge to cross the Sam Houston Tollway, or the ship channel in Houston, the alignment for the project was about 17,500 feet long, or 3.3 miles, and they drilled 20 borings, ranging from 120 to 200 feet deep. They had a boring roughly spaced every 875 feet. It wasn't quite laid out like that. But if you think about that, they investigated about 0.05%. The alignment, if you assume again a half-foot diameter boring. Now, that leads to subsurface cross-sections that look something like this. Hopefully you can see all these question marks, okay, on here. And all they're trying to show with these question marks is, hey, look, yeah, we had a sand layer show up in this boring, and then it didn't show up over here, and it didn't show up over here. So we really don't know what's going on. Or, we had some superficial deposits here, fill, or whatever we want to call this. Okay, I don't have the key, sorry, but, it was a couple of feet thick, and over here it was like 20 feet thick. So what happens in between? Well, we just draw some straight lines, right? We connect it with straight lines. We all know that geology isn't really like that, but we have to make these assumptions when we don't have tons of information. By the way, they drilled 35 additional borings prior to construction along this same alignment, so they ended up with about 0.16% alignment investigated. Now, that's just a little bit of background information to get you thinking about the problem of generating more information to use for geotechnical engineering, more information about the subsurface. So I'm a PI, a principal investigator on the Neary at U, Texas, a large mobile shaker site. This is an NSF-funded shared use equipment facility. And we have these great big shaker trucks that we take around and help various researchers study things like subsurface imaging or in situ nonlinear testing, soil foundation structure interaction. The video you can see playing in the lower left is kind of a schematic of the vision for performing higher resolution two-dimensional imaging. We do this type of work to a certain extent. We might tow some receivers behind a vehicle. We might hit on the ground with a sledgehammer or an accelerated weight drop, or maybe if you really have a lot of money, you might have a shaker truck that you could use. But the idea would be to try and be able to move along and develop an image of the subsurface. But the way that we do this right now is not super accurate. In fact, unless we're using a technique called full waveform inversion, it's pseudo two-dimensional profile, meaning it's still one-dimensional. We're just creating a two-dimensional image by stitching a bunch of 1D profiles together. So there are ways to do true two-dimensional and three-dimensional subsurface imaging, but it requires pretty dense arrays, like grids of sensors, with lots of what we call shock points in between all the sensors, so that we're sending waves in from all kinds of different directions, and we're sensing those waves with lots of receivers. So I'll talk more about this imaging today. But why are we imaging with stress waves? You've probably heard of methods like electrical resistivity tomography or ground penetrating radar. Those are definitely geophysical methods that are used on engineering projects, and they're very valuable for certain types of projects. I haven't really gotten into those methods very much. I tend to focus on stress waves, and there's a reason why, because we're not just wanting to develop an image of the subsurface picture, but we want to retrieve engineering design parameters from the subsurface. So I can't do any settlement calculations with resistivity values of the soil. They can help me identify soil types, and that's valuable, but I can't calculate deformation from electrical resistivity or from ground penetrating radar images. But with seismic images, I can. So the first thing I want you to think about is a direct simple shear test, where we're taking soil and we're shearing it, right? And we run the test, we get a stress strain curve. We're going to say shear stress here on the vertical axis versus shear strain on the horizontal. So this would be we'll just call it a quote unquote typical curve. It's a strain hardening curve, where the soil has kind of somewhat of a linear portion and then kind of a peak strength that just flattens. We don't see any reduction in strength like we might see with a strain softening type soil. But if you were to look at this stress strain curve and fit a line to the initial, what we call tangent modulus portion of this curve, we would be able to resolve what we call the small strain shear modulus, Gmax. Now, soils are extremely nonlinear. In fact, they only behave linear up to a shear strain of about 10 to the negative 3%. So really small number. Okay? So really, you can't even measure Gmax in the lab very accurately using traditional methods. If you use something like Bender elements in your specimens, you can measure. But if you're trying to measure with standard deformation techniques, you won't be able to measure Gmax. Okay? But we can measure. I need to be careful how I say that. There are tests that we can run in the lab, like the resonant column test, for example, that we can measure strains in this small of a range, but not with something like even a triaxial test or a simple shear test. Okay, but by sending waves through the soil, specifically shear waves, okay, we can calculate Gmax through this elastic modulus equation. The shear wave velocity squared times mass density is equal to the small strain shear modulus. So if we measure wave speeds in situ or in the lab, we can back calculate the small strain modulus. And that's a really important parameter to anchor all of our constitutive models, okay, that we use for example, finite element modeling or seismic site response modeling. Now, it's nice to have more than one elastic modulus, because if we can get a couple of elastic moduli, then we would be able to calculate the response ratio, we can get Young's modulus, we can get bulk modulus, all kinds of different helpful modeling parameters. So if you think about a standard odometer test that you would run an incremental load test for consolidation, and you're calculating, oftentimes in geotechnical engineering, we use the slang an E log P curve. Okay, you're going to use this to calculate consolidation signal. You can, instead of presenting the information from that type of test as void ratio, you can plot vertical strain versus stress. And then if you were to rotate that more like stress on the vertical axis and strain on the horizontal, then you get something a little bit more similar to what we're looking at for a shear test. So the slope in vertical strain versus stress space, MV, the coefficient of volume change, 1 over that is the constrained modulus. So when we're doing consolidation, settlement calculation, we're using the constrained modulus, but we might not think of it like that. Or often we're using C sub C and CR, the coefficients of consolidation for the recompression curve and the compression curve. But really, it's the constrained modulus. We're just looking at it in a different way. So the cool thing about that is if we measure P wave velocity, VP, we square it and multiply by mass density, we get the constrained modulus, the small strength constrained modulus. So by measuring the speeds of these waves in situ, we're resolving moduli. And if we have moduli, we can use them for stress strain deformation calculations. We can use them for dynamic calculations, like wave propagation, but we can also use them for static calculations, like settlement. Okay, so with that introduction, let me quickly explain where I'm going to go. I'm going to be talking about, first of all, a method called single station HVSR. That stands for horizontal to vertical spectral ratio measurements. I'm going to be talking about resolving, being able to directly measure fundamental resonant frequency of the site. I'm going to be talking about using those measurements to create what we call pseudo 3D subsurface models, large models ranging up to several kilometers in each direction, and being able to do it cheap and fast, with maybe a couple days of field testing at the most. I'm going to talk about surface wave testing, really kind of more of a state-of-the-art case where we're profiling over 500 meters deep at pretty good resolution, comparing that to borehole measurements. We're using methods like MASW, multi-channel analysis of surface waves, and then a method called MAM, passive microtremor array measurements. I'm going to be talking with challenges for linear array, passive methods. You might have heard methods such as REMI or passive roadside MASW. And those techniques have some pretty significant uncertainties associated with them, so I'll talk about that. And then I'll talk about kind of the latest and greatest type methods like full waveform inversion and using advanced sensing technologies like fiber optic, distributed acoustic sensing for generating true 2D or 3D subsurface images. Okay, horizontal to vertical spectral ratios. How many people in here have heard of HVSR testing before? Raise your hand. Not very many. That's kind of what I suspected. So this is the easiest test you haven't heard of before. Okay? It's not difficult to perform. You take a 3-component seismometer. So you've got an X, Y, and Z component. You put it on the ground surface, and you sit there for 30 minutes and record ambient vibrations. You don't have to do anything. You can sit in your car if you want. If it's snowing outside like today, you turn on the heater and you just wait. Okay? Now, after you've completed that 30 minutes to an hour of listening to the vibrations in the ground, you break those recorded signals. These are just the noise time histories here. You break them up into windows, maybe 30 seconds to 1 minute long. And for each of those windows, you perform a Fourier transformation. So you go from the time domain to the frequency domain. You calculate something we call the Fourier amplitude spectra, the FAS. You then take the ratio of the horizontal FAS divided by the vertical FAS, and you get this nice curve we call the horizontal to vertical spectral ratio, or the H over V ratio. And oftentimes there's a peak in this H over V ratio that occurs at the resonant frequency of the site. Now that's pretty great, okay? Because the resonant frequency of the site is a really important parameter for many studies, especially for earthquake engineering. I mean, I'm an earthquake engineer at heart. I do lots of different things. But even if you're not really interested in earthquake engineering, if you measure the resonant frequency of the site, and then you have some idea about the geology, for example, like maybe you have some residual soils over rock, okay? And you want to see how the rock is varying across the site. You can make an assumption about the average shear wave velocity, or maybe even make some shear wave velocity measurements in a limited area, and then you can do a bunch of these H over V measurements, and you can back calculate the thickness of the soil over rock using these H over V measurements, for example. That's one thing you can do. So the types of sensors that we use for H over V testing, you can use a wide range of sensors, ranging from expensive to cheap. So the ones that I tend to use are broadband seismometers. These could cost anywhere from $10,000 to $15,000 a piece though. I use them for other purposes, not just HVSR testing. Or you could use high frequency geophones. You could get one of these 3-component geophones without the data acquisition system for on the order of probably $500. Something like that. So there's a wide range of quality of sensors that you can get. If you got the cheaper ones, you wouldn't be able to measure to as low frequencies, but that would only apply for really deep, really soft sites. Also, you can run these types of measurements on paved surfaces. It's better if you can bury them in a really small hole. You can see this is from a picture, I think this was in Anchorage, Alaska, and this sensor is literally about this big, just a little bit bigger than this water bottle right here. So they're not too big. You dig a little hole, compact the soil around there, and you'll get even better measurements than if you just set them on the surface. So we have, this is an open source software, by the way. It's called Geopsy. It's written by one of my colleagues at the University of Grenoble in France. And so if you want to play around with HVSR testing, there's some software you can just download. It's free. You don't have to buy anything. And you can walk through this traditional processing, which I'm not going to go into in a lot of detail, but you'll be able to statistically resolve this, this peak right here for all the different time windows that you break your noise recording out into. So let me talk just briefly about fundamental frequency. I'm going to escape old screen sharing stuff too. Okay. Let's go back here, share screen. Okay. So I love this video, one, because it's a great song from Metallica, and two, because it's just really cool to see the resonant frequencies set up in these strings. So who in here plays a musical instrument, like a stringed instrument? I see a couple of people. Professor Wu played the piano, so he would have understood resonances extremely well, right? So if you think about the thick strings, they're playing lower frequency notes, right? Longer wavelengths, if you look at the lateral distance between peaks in those waves. And then if you look at the thin strings, they're higher frequencies, right? And they have shorter wavelengths. The peaks are closer together. So musicians really understand resonance as well. If you want to further change the note, instead of plucking a different diameter string, you would change the length of the string, right? So interestingly, let me see if I can close this. Here. The soil deposits are just like those guitar strings. They all have resonant frequencies as well. You've got the soil over, we'll just say bedrock, and there's a pretty wide range of definitions of what rock is, but we'll just say soil over rock. So the thicker the soil is over here, the lower the resonant frequency of the ground. The thinner the soil is, the higher the resonant frequency. But then if you look at the different compositions of the soil, gravel, silt, sands, clays, etc., like those would be kind of like the diameters of the strings, right? Only it's a really complex combination of all those different diameters. But if you pluck the ground, like when an earthquake happens, the ground's going to resonate. And for example, if I did some H over V testing here in this area, I might measure a curve that looked like this. There's a peak here of 20 to 30 hertz. This is a curve from a real site, by the way. No, schematically here. So you can get the resonant frequency of that location. You could make an H over V location or a survey over here, and you can get the resonant frequency of that site. The amplitude has a meaning. I'm not going to talk too much about it. We don't 100% know exactly what the amplitude means, other than the higher the amplitude, the more it's going to resonate like in an earthquake, but there's not a one-to-one correlation. So mostly we're just looking at that frequency, okay? And then if you look at the resonant frequency of your buildings, you ideally would prefer that those not match, right? That's a double resonance condition. That's what's caused a lot of buildings to fail in earthquakes around the world. And so as a seismic designer, you have to try and make sure that if you do have a situation like this, if your building is sitting over here on these deeper soil deposits, its fundamental frequency is pretty close to the fundamental frequency of the soil deposit, and that could mean you're going to have to design for really high base shears. You're going to have to kind of be able to resist significant lateral loads. But over here, that same exact structure would not have very much amplification from the ground at all, and you wouldn't have to design for as high of lateral forces. So I'm going to just skip over this for a minute. Here's a simple application, okay, where we've used this in the past. This is from, in 2016, there was a big earthquake in New Zealand called the Kaikoura earthquake. And this is the port in the city of Wellington. Their port was heavily damaged by this earthquake. It's pretty fascinating case history. They actually had gravel liquefaction during this earthquake. So big pieces of gravel came out of the ground. So not just sand, which we know can liquefy, but gravels. And you can see here's a bunch of receivers set up. This is me. We're doing some MASW testing here. But also, all of these dots over here in this picture, every one of these dots represents a place where we put one of those H/V stations down on the ground. And we don't have this many sensors. Actually, we have a lot of them. But at this point, we were using 10. Okay, so there were about 5 of us. And we would just walk around the port at night when it was closed, and every 30 minutes we would move the sensor to a new location. So with 5 people and quite a few hours of testing, we did most of this testing in like 1 or 2 days, because we couldn't work during the middle of the day when they were trying to run the port. But what you see, the colors now for each one of these dots represent the fundamental period. Now this is just the inverse of frequency, okay? So T, or period, is 1 over F. So if you think about short periods, those are high frequencies, and longer periods being lower frequencies. But what you see is like there's some shorter period fundamental ground frequencies in this area of the port, and then the soil gets deeper. Okay? The period is elongating. That means that it's softer overall. The system response is softer. And so this is an area of deeper material. And you get up here close to this area, and something kind of interesting happens over a very short distance. We're going from periods on the order of 2 seconds to on the order of 1 second in a very short amount of time. So what happened? A large vertical offset. If you go back and you think about that equation where height is part of the thickness of the soil column is part of the equation to calculate the resonant frequency, we found a fault. We found a vertical offset of a fault that they didn't know was there. It was kind of inadvertent. We weren't planning on doing this. We were just looking to build a numerical model to use for seismic site response. Now they know that the fault called the Wellington fault runs right over here, but it looks like it's either mislocated or there's a splay of the fault that runs right through the port up here. So we kind of inadvertently found this. Well, H/V testing can be used to provide quantitative information, or it can be used to provide qualitative information. If you're just looking for anomalies, like a channel or something, it's pretty easy to just run a line of H/V measurements out across there, and you'll be able to see how the resonant frequency is changing. And that could, you might not care what the resonant frequency is in and of itself, but you might be able to locate underground anomalies like this. Something that you know is there, that you don't know it's there, but you're just looking to find the location. Okay, so here are 3 papers and a Python package that we published recently, and a web app. Ooh, a lot of stuff on this page. So this Python package and this web app, they have incorporated all of the methods that we discuss in these papers. Me and one of my students named Joseph Van Tassel, Tangent Chang wrote these papers. But the point is if you want to play around with HVSR testing, you can download this Python package, or you can download or go to this website. Now, if you want, right now, you can scan this QR code with your phone. You can open up the web app. There's some demo data. I'll just run it here real quick. There's several example files that we've collected and put up there so people can kind of play around with processing. But it's pretty, I don't know. We use the web app just for like demonstration purposes. If we really want to crunch some numbers, we obviously use the Python package, but this would be in lieu of using the Geopsy software that I told you about earlier. This has some other features in it, a little bit more statistical analyses of HOV testing. So I'll kind of leave it like that. I'm not trying to give you too many details. I just kind of want to let you know about tools that are available for you. So you want the address? Yeah, there you go. hvsrweb.designsafe. So DesignSafe is an NSF-funded data storage facility. They also have other tools that are available on this website for natural hazards engineering. You're welcome. Okay, so let's look at something else we could use these H/V measurements for. We've developed a method we call the H/V geostatistical approach for building pseudo 3D VS models. So they're 3D velocity models. We found them to be extremely useful and helpful to us, but they're not true three-dimensional models of the subsurface. So there's a lot going on here. I'm going to just use a case history to kind of illustrate what's happening. So we developed this method primarily to use it at what we call borehole array sites. A borehole array site, there's not tons of them in the US. There might be 20 to 25 of them, but they're areas where we've drilled pretty deep boreholes, okay? And we've installed strong motion instrumentation or weak motion instrumentation to record earthquakes at multiple levels, multiple depths in these boreholes. The reason we do that is because we'll have a recording station at the surface that captures the earthquake, but we'll also have recordings at depth, and sometimes significant depths, over 100 meters or a couple hundred meters, so that we can capture the earthquake waves while they're still in rock, hopefully. And then as they propagate up through the soil, we can look at the amplification between the rock and the soil surface and see how our modeling does representing what's actually recorded when we know the input. So at these, there's two borehole array sites we've developed these pseudo three-dimensional array models for. One is called the Treasure Island Downhole Array here in the San Francisco Bay. The other one is Delaney Park Downhole Array in Anchorage, Alaska. I'm only going to talk about the Treasure Island Downhole Array today. So those of you who have been to San Francisco or Oakland, this is the Bay Bridge that goes between Oakland and San Francisco, and it passes right over Yerba Buena Island. Okay? Now, Yerba Buena Island is a natural rock outcrop in the middle of the bay, and Treasure Island is an artificial fill island that was created 1912, something like that. There's a World's Fair in San Francisco. Can't remember, that's when it started, but it's a large man-made island. You can see it in the background, Treasure Island, Yerba Buena Island. So Treasure Island, during the 1989 Loma Prieta earthquake, there was pretty significant liquefaction on Treasure Island. There's kind of some famous ground motion recordings that lots of students have used over the years, where there was a recording of the earthquake on Yerba Buena Island and a recording of the earthquake on Treasure Island, and they're very different from one another, even though they're very close together. And so in your geotechnical earthquake engineering class, your professor would often say, okay, given the earthquake recording at Yerba Buena Island, numerically model the subsurface and see if you can predict what it was like on Treasure Island. And then you'd compare your modeling results with what was recorded, and you'd find you did a horrible job. And that was kind of the purpose of the exercise. Anyways, so one of the reasons why we felt people weren't often getting the modeling right at Treasure Island is because they were using a one-dimensional modeling approach from a point measurement. And so here's the middle of Treasure Island where there's this borehole array. And we've recorded numerous earthquakes since 1989 using this borehole array, most of them small. But we went to Treasure Island and we used H/V testing, and we put a bunch of sensors all over the island. We couldn't get into this area because this is being redeveloped right now. Massive ground improvement project going on here. Pretty fascinating work. And they're basically going to put some high-rise structures out here and some big buildings. Very valuable land. Anyways, you can see that the lower frequency information, a lot of the island has very similar H/V values, okay? So that the fundamental frequency is on the order of 0.6 to 0.8 hertz for much of the island. But as you get close to the causeway that leads to Yerba Buena Island, the fundamental frequencies go up significantly, meaning it's stiffer over here. And it's stiffer because, I mean, the whole island's basically made out of the same material, but this is a lot shallower. And if it's shallower, then it's a stiffer response than if it's deeper. So we could start to see that there were pretty significant changes in the fundamental frequency as we got closer and closer to Yerba Island. So what we did is we took these F0 values from H over V testing. This took us, I mean, we were doing some surface wave testing too, which I'm going to talk about later, but this took us less than 2 days, let's say a day and a half, to get all of these measurements with like 4 or 5 people. And then we used geostatistical kriging, where we krigged those discrete measurements, and we came up with a pretty smooth value with, I think, cells on the order of 50 meters, about 50 meters. So we could predict what the fundamental frequency was everywhere where we didn't make measurements. Once we had that, okay, at the location of the borehole array, we had one shear wave velocity measurement in a borehole. They measured this using a technique called PS suspension log. So they measured shear wave velocity down to the top of the rock, which is right here at about, let's just say 90 meters below the surface. And then what we did is we knew the fundamental frequency of the soil column where we measured the shear wave velocity. And then we knew the fundamental frequency everywhere else, and we just created a ratio between those two. And we applied that ratio as a scaling parameter so that we could take this measured shear wave velocity profile in black and create a pseudo shear wave velocity profile everywhere else in this grid. So through doing this, then, we can create a 3-dimensional model of shear wave velocity, and we can kind of see how the bedrock depth is changing across the extent of the entire island. By the way, this is an area about 1.5 kilometers by 1 kilometer, just to give you an idea about space. It's quite a large area. Now, with this 3-dimensional model, you might say, okay, that's great. Does it work? Is it any good? We're kind of making some assumptions here. So we've used this model in multi-dimensional site response analyses, where we're trying to predict the recordings at the surface from the input motion in the borehole array. And we use this software called Seismo VLab. Okay, it's an open source finite element software. I'm not going to get into all the details of the boundary conditions and the damping and all different things that we had to do. But let me just say, if we took and did a 1-dimensional analysis using the measured shear wave velocity at a point from PS suspension log, and we calculated the theoretical site response, okay, we call this the theoretical transfer function here in blue, and we compared it to the measured site response, which is shown in black, we would always find that we were overestimating, and this is a log scale, okay? We're overestimating the amplitude significantly using a 1-dimensional analysis. So what we did is we're like, well, how big of an area is influencing the site response? So we took our 3-dimensional model and we generated different cross sections of different azimuths. I'll only talk about this cross section in the X direction. But we looked at an area then expanding away from 1D. We looked at an area that was 100 meters by 100 meters. And we created a 2-dimensional model using the pseudo 3D VS profile. We ran 2-dimensional finite element wave propagation simulations, and it dropped the amplitude down a little bit, not very much. So we expanded it to 600 meters total, 300 meters in each direction from the borehole. When we did that, the amplitude came down quite significantly. So we're like, well, the earthquake must be sensing a pretty large area. And this 1-dimensional assumption isn't working very well, even though Treasure Island's the most 1D site you could hope for. It's man-made, hydraulic fill, it's a beautiful site, but the earthquake doesn't think it's 1-dimensional. Okay, so we kept enlarging our model. As we went further, nothing much happened. And then when we got out to the full extent of our model, meaning we were modeling the entirety of Treasure Island, we saw something very interesting. Right? So until we start incorporating this shallowing bedrock over here, which is indicated by these higher F0 values, we didn't see this secondary peak that's generated. And I can talk about why that's generated, but I don't think I want to get into those details right now. But this is a pretty interesting conclusion that if you really want to model the seismic site response at this point in the middle of this big flat island, you have to use a model that covers the entire and not really covering the entire island, that's not that important, but you have to capture this shallowing bedrock over here. Because as the earthquake waves come up, they hit that shallow bedrock, they're traveling faster on this side through the bedrock, these waves have to go through the soil, it creates inclined waves that go up and travel across the surface waves, and those are what cause the secondary peak. So we didn't match it perfectly, but we got really close. Right? And we're still working on three-dimensional modeling of this. So these are some of the things that you can do with these non-invasive testing measurements. If you're doing certain work, you can't just go and drill boreholes in your neighbor's property, right? Like, how do you develop a model that's 1.5 kilometers by 1 kilometer? You have to use non-invasive methods. You can't just say, hey, I'm going to come over and drill a 120 meter deep borehole here and here and here and here. Your site might only be 50 meters by 100 meters or something like that. So non-invasive methods can be very valuable. What time did I start talking? You guys tell me when it's time to just sit down and be quiet. I have 15 more minutes. That's great. Okay. I've covered 1/3 of my slides. This is typically what happens. Don't worry, I'm not going to force you to listen to everything, okay? When it's time to stop, we'll stop. Let me tell you about surface wave testing, okay? So early in my career, Patrick mentioned I got this award from President Obama. He was a lot taller than me, by the way. Okay? Like this. It was a really cool experience, but that's not why I put this picture in there. The reason I put this picture in there is because when I wrote this proposal that I ended up getting this award for, clear back in 2010, I wrote, traditionally, surface wave methods have been used to provide a single deterministic VS profile, a single profile over here, okay, for each site tested without consideration given to uncertainty. An ever-increasing number of researchers and practitioners are using surface wave methods without understanding the uncertainty in their results. And this is the kicker. It's likely that no other non-standardized test is used in geotechnical engineering more widely than surface wave. So, how many people in the room have heard of surface wave testing? Few more than H over V. Okay. MASW, that's probably the most common type of surface wave testing. What about MAM, or micro tremor array measurements? What about REMI or REMI? Okay. Interesting. So you do know there's no ASTM standards for surface wave testing, right? It's kind of interesting, right? There's a reason why. It's pretty hard to write standards. There's people selling competing software. And man, you get those people in the room together and they don't want to agree about what should be in a certain ASTM standard, especially if it might disadvantage their business interests, right? Okay, so the state of the practice is deterministic, I would say. You're given a single answer, or it might be a single, nice, beautiful, colorful 2D image with lots of blues and reds and stuff on it, okay? But let me just tell you that the process that we go through to get that image has a lot of uncertainty in it. And if people aren't giving you some realistic discussion of uncertainty, then you might be not understanding that image may not be a realistic representation of the subsurface. So this is a good paper. If everyone would follow these guidelines, it would help. So while we don't have ASTM standards, we do have guidelines for the good practice of surface wave testing. I'm one of the co-authors on this paper. This was an international team of researchers, and we published this back in 2018 after a big kind of project we ran in Europe. But if you're wondering if the work you're doing or the work you're paying someone to do is consistent with these guidelines, you should look at the guidelines and see. It's a good resource. So surface wave methods. There's a bunch of them out there under different names. I asked you for some of the names. So under active source methods, the original type method, I would say, was developed by my former advisor, Ken Stokey, the spectral analysis of surface waves. That was really pioneered in the early to mid 80s. They were using it for pavement testing initially, and then they started using it for testing much deeper. And then in 1999 and 2000 really is when multi-channel analysis of surface waves came out. And then passive methods, have been around for quite a while, but really haven't gotten very popular until recently. I would say the refraction microtremor method, which uses a linear array, was the first passive method that was really delivered to the people, so to speak. Okay? By the way, I hope to get to this later, but I'm running out of time. This method has a lot of weaknesses. Okay? I've written several papers about this, and I cannot recommend using this method for engineering purposes. Okay? The microtremor array method, which uses two-dimensional arrays, so that you're able to resolve the direction the passive waves are coming from, is a much more theoretically robust method. So my standard approach involves MASW and MAM. Now I'm going to skip over a little bit of background information and just say that surface wave testing really comes down to 3 steps, all the mystique. Okay? You're collecting data in the field, the acquisition stage. You're processing it to get something we call dispersion data, and then you're inverting dispersion data to get a shear wave velocity profile. Anytime you hear inversion, you should start thinking in your head, non-unique, non-unique, non-unique. You're solving an inverse problem. I'll give you an example in just a minute. But we also have open source tools that we've published to help with processing. We have a Python script we call SW process, and an accompanying journal paper that talks about how to rigorously process surface wave data, MASW and MAM. We have an open source Python code that's related to performing inversions. Okay, so this paper is called SW Invert. It's a workflow for performing inversions. Everything that I do in my research group can be duplicated if anybody is willing to put in the time to study up, because we've made the software available to anyone that wants to use it. So we're not holding anything back. Like literally everything that I do in terms of surface wave processing can be done by others. The knowledge, yeah, you need knowledge base, but the tools are out there. So let me just quickly, in the interest of time, I'll give you a case history, okay, and how we use these methods. This is for a greenfield site for a nuclear power plant in Georgia, the Southern Company. I don't think this is going forward, but we at least did the site investigation. Okay? So as part of that study, we did some MASW testing here in this area. We had a linear array of using 48 vertical geophones spaced at 2 meters. Then we had these MAM arrays, these broadband seismometers, which we can also measure H over V at, each one of them. And we put the sensors in circular shapes. Okay, so that with a circle or a triangle or an L, your array now has 2 dimensions to it, and you can resolve the direction that the ambient noise is propagating. You can't do that with a linear array. So with a linear array, it's impossible to tell where the waves are coming from. And if you can't tell where the waves are coming from because you're not generating them, then you have to make assumptions. And those assumptions can often cause bad data that you may not know about. So if you use a 2-dimensional array, it's much more robust. It doesn't have to look like this. This is a pretty special site. You see that this array is over 1 kilometer in diameter. So with these recordings, I'll skip the multi-dimensional Fourier transformation, if that's okay. Is that okay right here? Right now? Okay, all right, we'll skip that. Stuff about processing. Okay. So we extract dispersion data. Again, in interest of time, I'm going to go through this quickly. Let me talk about inversion for a minute. I'm going to skip this too. Let's talk about this. This is better than multi-dimensional Fourier transformations. What equals 9? What is the correct mathematical expression? So who can give me a mathematical expression that equals 9? 9 equals 9. I like that. Occam's razor. The simplest answer is the best answer. Okay, good. Anybody else? What equals 9?
2 times 9.
What's that?
3 times 3.
3 times 3. Somebody give me an addition.
2 plus 7.
Okay.
8.6 equals.
Oh, maybe in Geotech, I agree. Okay. 7 might equal 9 in Geotech.
I know, right?
You get the point. There's a lot of answers. Okay. 6 plus 3, 12 minus 3, 27 divided by 3, 3 times 3, square root of 81. So this is an inverse problem. I gave you an answer and you're trying to tell me what the expression is. Okay? So when we're doing surface wave inversions, we measured something. That something isn't really what we want. We want the properties that control that something. So we're going to make a guess about what the subsurface looks like, and then we're going to solve this inverse problem. But if I told you it was an addition problem, would that help limit the non-uniqueness? It would, right? So if we can feed these inversions some supporting information, that would be helpful. Like if we can use borehole data, or if we can use cone data. The problem is if we're looking really deep, we soon run out of information to help us constrain this. H over V data can help us constrain. Geologic information can help us constrain. Okay, but let me talk about, so what we did is we did some inversions of this data we collected at this site in Georgia, the Greenfield site, and our results are shown here in red, okay? So I don't ever provide one answer. Actually, if I go back one slide, when I give people data, there are 400 shear wave velocity profiles here that go down to 700 meters, okay? So I give people statistics, and I say, look, the median of these profiles looks like this, but I can't give you just one answer. I can tell you a range of where I think bedrock is, 500 meters below the surface, and I can calculate statistics on where I think that depth is, but I'm not going to just give you one answer because this is an inverse problem. And if I think I can give you one correct answer, that's not honest. It's not a fair assumption of what's actually taking place. But at this site, they drilled a borehole over 600 meters deep. You can see it's starting at elevation plus 100 some meters and going down at elevation negative 450. And these blue lines represent measurements that were made in that borehole from PS suspension logging. The red lines represent our MASW and MAM surface wave inversions. And this green line represents some SASW data that's processed by Ken Stover using a great big shaker truck. So with ambient noise, I mean, the MASW gave us the top 15 meters. Okay? The ambient noise is what gave us everything else. It's pretty cool to think that you can just set these sensors out on the ground, and with pretty advanced mathematical processing given, you can develop these profiles that go all the way down and tell you where bedrock is 500 meters below the surface with quite a pretty good degree of accuracy. Okay, so what time are we stopping? 10 minutes ago? 10 minutes from now? 2 minutes.
2 minutes. Yeah,
2 minutes.
But you can go a little bit longer.
No, let's see. You guys are probably bored already. Okay.
We have a lot of questions.
We'll have a lot of questions. Good. Okay. Let me say a word about passive source linear array methods. Okay. So REMI, there's another method called passive roadside MASW. These have been marketed to civil engineers with great vigor. Okay. Passive arrays measuring ambient noise, often in the near field next to a road. All of these things are a dangerous combination. Okay? So they will tell you that you can learn how to do this testing in a half-a-day short course and that you're going to get great results. And I'm just telling you that there is a huge potential for mistakes using this type of method. Okay? I'll leave it at that. Theoretically, you can't argue with me that these are robust. Okay? There's no way that we can have that argument and I won't win. Okay? But in some cases, they work reasonably well, but it's by serendipity. Okay? It's not because it's a theoretically robust method. So if you're using these types of methods, you should talk to me. All right. In that good practice, those guidelines that I talked about earlier, Thoki et al. 2018, good practice is surface wave analysis. The use of passive source linear array methods is quote unquote strongly discouraged. So while we don't have ASTM standards, we do have guidelines established by experts across the world, and those types of methods are strongly discouraged. Okay, pseudo 2D MASW testing. It can be done, okay? But it's pseudo 2D, it's not 2D. You're still doing MASW, it's a one-dimensional method. You're averaging everything within the extent of your MASW array, and then you come up with a 1D representation of everything within your array, and then you pull forward and collect more data, and you're stitching these together and creating a two-dimensional profile. If done rigorously, it can be quite accurate, but still there's uncertainty. If not done rigorously, you might get nothing that looks like the subsurface. In the aftermath of the Christchurch earthquakes in 2010, 2011, a company in Christchurch, New Zealand, convinced the city, the government in New Zealand, that they should perform 2D MASW testing across the entire central business district. They collected kilometers and kilometers of these two-dimensional shear wave velocity profiles. They submitted the data, okay, and when all the geotechnical engineers in the city started looking at the data, they're like, this is ridiculous. This doesn't look anything like what we know the subsurface looks like, okay? There are very strong marker geologic features in the subsurface that they knew existed, and these nice colorful pictures didn't show anything like that. Okay? So you can get results that are not realistic representations of the subsurface, so just be careful about that. All right, last topic, full waveform inversion. I'm going to buzz through this so fast. Okay, one of the really cool things that we're experimenting with right now is called distributed fiber optic sensing, distributed acoustic sensing using fiber optic cables. So instead of putting traditional seismic sensors like geophones on the ground, we can stretch a fiber optic cable out and maybe bury it just under some loose surface soil, or get a trenching machine and just put it in a shallow trench like you did for a sprinkler system or something like that. You put the fiber optic cable in there, and now you're making continuous measurements with a spatial resolution on the order of like meters, but over kilometers. It's really a really cool sensing technology. We've used that sensing technology to perform what we call full waveform inversion. Full waveform inversion is a true two-dimensional or three-dimensional imaging method. It has higher spatial resolution than surface wave testing, theoretically, but it's even more complicated and more challenging to perform than surface wave inversions. If surface wave inversions are non-unique, full waveform inversion is very unique. So you have to kind of know what you're doing. But you're essentially trying to match some observed waveforms with simulated waveforms. And those simulated waveforms have been developed through finite element or spectral element methods, finite different methods, where you're simulating complete wave propagation. We use a software called Salvus. This one is not open source. We have to purchase it to use it. It's pretty complex software. This is a test site called the Hornsby Bend Test Site in Austin, Texas, where we had 200 meters of fiber optic cable spread out on the ground. And then this is one of our shaker trucks, our little shaker truck. We call that one Thumper. And we did shots all along the cable about every 8 meters. So there's 32 shot locations. And then we take the recordings all along the cable for every single shot location, and we invert it to get an image of the subsurface. Now we've drilled 2 boreholes at this site, one shown here, one shown here. I didn't talk about it very much, but we also pushed a bunch of cones along the alignment. So we know what the subsurface looks like here from invasive measurements. So here are some of the example waveforms that we've collected with different shot locations, just 3 out of the 32 along the array. We developed starting models. These look like nice, colorful images of the subsurface already, but these are just our initial guesses. Okay? We've developed them using MASW, downhole seismic testing in this borehole right here, a convolutional neural network approach, which I don't have time to talk about, our machine learning type methods, and 2D MASW. So we start with those models. We generate synthetics by propagating waves through the models. The synthetics are the blue lines. Our observations are the black lines. And originally, the best model is either the 2D MASW or the CNN model because they have the lowest misfits. We then perform a lot of stages, a lot of iterations where we're changing the subsurface and trying to get the simulated waveforms to match the recorded waveforms. And you can see ultimately we had misfits that were as low as 1.9, 1.8, 1.4. These are all pretty equivalent misfits. So if we want to look at what the final models look like, they're not the same. But if we'd only used one starting model, we would have got one of these answers, and we could have given it to you as a class. But because we used 4 different starting models, we got 4 different answers. Now there's some similarities between some of the models. The near surface velocities are pretty similar. on the order of 200 to 300 meters per second. But these boreholes show the lithology, okay? There's a shell layer right here, that's 13 meters, and it's pretty consistent, at least in these boreholes. This is the depth of CPT refusal across the site. And so the model that we used downhole to start with is probably, in my opinion, the least accurate of all of them. And you would think that if we used an invasive method to measure shear wave velocity and then use that as a starting model for this full wave inversion, it might give us the best results. But in my opinion, the one that looks probably the best is the machine learning approach, which I didn't have time to explain how we did this. But you're looking for a strong contrast right here at the interface between this shale, or this clay sand or clay gravel and the shale. And we're kind of seeing that with this full waveform inversion model. So this is a continuous two-dimensional profile over 200 meters. It's too bad this site was so uniform. It would have been nice to have a site with like a channel in it or something like that. But these methods are out there. I just want you to understand that while we can do this, that there is some non-uniqueness associated with it. And before I quit, this is my last slide, I promise you. This is a data set we collected in Florida, a site called the Newberry site. This site has all kinds of karstic voids under it, like crazy amounts of voids. Okay, and we installed 2 kilometers of fiber optic cable at this site, like weaving back and forth, and like a grid pattern. And then we used our great big shaker truck T-Rex to generate hundreds of shot points inside and outside of this grid. And we're using full waveform inversion to image the subsurface using, if we can't do it at this site with all of this work, it cannot be done. I promise you that, okay? Because we have so much instrumentation and so many shot points, 3-dimensional shaking from a large fiber-sized truck. But this data set is 1.2 terabytes. And if you want, you can download it. It's open access. You can play around with the data. We published it free for everybody because if we work as a team, then we can do it. Yeah, you want the data? You got it. It's also on Design Safe. Okay, so I'm going to end with that and just say that for 1D VS profiling, I feel pretty good. Like, I finally feel like I can do 1D imaging. I can quantify uncertainty. I can give you deep profiles. I can give you profiles over the top 15 meters, or I can go down to a kilometer. Like, I feel pretty good about that. And if you follow a lot of the papers we published, like, you can quantify uncertainty. But I see a lot of bad practice out there still for 1D. Okay, for 2D profiling, pseudo 2D profiling, yeah, it can be done. But if your 1D is bad, how is your 2D going to be good? It doesn't work that way. Okay, so if you're not doing a good job at 1D, your 2D won't work. And then true 3D imaging, 2D and 3D imaging, it can be done. We're making progress. We're using full waveform inversion. We're using machine learning methods. But man, I don't think this is something you want to try and practice right now. Like, it's not ready for prime time, definitely. It's coming. It's there in the future. For like really big jobs, yeah. But for standard stuff, no, don't try it. Not recommended. And with that, I will just take questions and say, if you're interested in surface wave testing and learning more, I'm running a 4-day short course in Logan, Utah, my hometown right now. It's between July 29th and August 1st of this year. And yeah, 4 days, you should walk away with quite a bit of confidence that you can do surface wave testing, at least for 1D and quantify uncertainties. Sorry if I went over, and sorry I rushed through the slides. I hope you learned something new today. Thank you for your time. Really appreciate it.
A few questions.
Things like, wow, you just forced water into us out of a fire hose. Yeah.
You mentioned the we might have to be one array or 2D. Do you have to run the 2D at the same time, or you can run separately?
So with either MASW or REMI or REMI, Okay, the most common way of generating a two-dimensional profile like this, it's really a two-dimensional profile along a linear alignment. So if you want to come back and get something perpendicular to that, you'd have to have another linear array going in this direction. Okay, so what happens is you can either do this with stationary geophones, or you can pull them behind a truck. So this schematic is showing them being pulled behind some sort of vehicle. But you stop your array, you might have 24 geophones, and they're attached to on a land stringer, we call it. It's like a piece of fire hose, and you drag them along the ground. And then every time you stop, you hit on the ground with some sort of source, you record waveforms, and you treat that like a 1D sounding. Okay? So you generate this 1D sounding, and then you pull forward, maybe by 5 meters, maybe by 15 meters, but some discrete distance you pull forward. You collect another set of data, you process it to get a 1D profile, and you keep doing that by marching along in sequence. And then you take all of the 1D profiles that look like this, and you contour them together to get a two-dimensional image. Does that answer your question?
Yeah.
Other questions? Yeah.
Brady, when I was in practice, we ended up doing a lot of suspension logging.
Yeah.
And typically it added about $10,000 per suspension logging on average.
Mm-hmm.
So it was really for medium to size projects that we could even afford to do that. Otherwise, for smaller projects, we had to do dynamic CPT.
Right.
What sort of projects do you need to have? What sort of budget do you need to have for some of these more advanced techniques like full inversion?
Yeah, full waveform inversion, if someone asked me to do it on a project, I'd just say no. Okay, because you don't have enough money to pay me to do it. It's that kind of money, for me personally. Now other people might do it.
But
Okay?
can you give us like a scale?
I can, a scale, MASW, okay? It depends on who's providing it, but you can find people who do MASW testing for me. The reason I pulled this up is, let's say the new ASCE 722, the new IBC. Now, for those of you who have to do anything with seismic, there's all these new site classifications. And there's a penalty. If you don't measure shear wave velocity, if you correlate it to blow count or tip resistance or something like that, now there's a penalty. Okay? You have to take your site class and you have to bump it up and down by 30%. You have to take like a window of the site classifications and take the worst case scenario. Okay, so starting whenever people start adopting ASCE 722, if you're anywhere where you have to consider seismic site classification, you're going to have to measure it, or there's going to be a financial penalty associated with that because you're going to have to design for higher ground forces. So if you wanted to get VS30, okay, for example, from surface wave testing, I rarely to never have been able to get VS30 using a sledgehammer and MASW. There will be people who will do it for you, but I don't think the results are very reliable. But if someone was to just do MASW to get VS30, they'd probably charge you like $2,000, something like that. Okay? Yeah, and the reason people like linear array passive methods like REMI or REMI is because they tell you that you can look deeper, which is true. Passive methods, you can generally look deeper, okay? But what I do to get VS30 reliably is I do MASW, and then I would just make an L shape out of my geophones, and I would create a two-dimensional array, and I would use MAM testing. And so if you're going to do MASW and MAM, it's going to cost a little bit more because you have to do more analyses, and people might charge you $3,000 or $4,000 to do that. I'm not in the market of competing with geophysical engineering firms or engineering consulting firms, so I don't know what the typical dollars are. I don't do normal testing like this for projects. I do this for like nuclear facilities. And so other people might have a better idea of the cost, but it's on the order of a few $1,000s. And then if you want to look deeper and deeper and deeper, it just costs more. Hope that helps a little bit. So, and that's to do the PS logging. Is that to drill the borehole too, or just to do the logging?
Well, for example, when we did suspension logging, we would use existing borings, then of course grout them, put the PVC pipe, so it would typically cost an extra, I would say just the suspension logging, it was maybe about $5,000, but we'd use the boring, including the grouting and all that. Probably quite often came to about 10,000 by the time we were done.
Yeah. Okay.
Remy, I think we used to pay about 5,000.
Wow.
And I'm talking about before I came here.
Yeah. Let's see.
On the first slide that you presented, the H/V testing, the green line of the soil resident frequency had a couple of peaks very close to the residence. And then later, when you were discussing Treasure Island, there were 2 peaks to the resident frequency. Do you think that's different mode shapes of the subsurface presenting in the resident frequencies, or do you have another theory for why soil behaves like this?
Yeah, great question. So one thing I didn't talk about was these 2 lines are from the different horizontal components, and usually we combine them into a single component before we calculate H/V. We can do like a squared average or geometric mean or something. But whenever you see what we call azimuthal variability in HVSR, and you have a different resonant frequency peak in one direction than the other, right away you know your site's not one dimensional, it's 2-dimensional. So you'll see that. We do these calculations I didn't show you, but we'll look at the H/V plotted as a function of azimuth, and you can see the resonant frequency changing. And that just means it's stiffer in one direction than in the other direction. And that kind of makes sense if you think about buildings. If you're a structural engineer, right, and your building's asymmetrical, it's going to be stiffer in one direction, have a different frequency than in the other direction. Subsurface is exactly the same way. So at Treasure Island, there's a buttress in one direction. It's being buttressed by Yergaboy Island, and in the other direction, it's not. So it's softer in one direction than in the other. And if you're doing site response analysis, you have to take that into account. Good question. Let's see, Todd, I think you got a question.
Yeah, thanks, Brady. It's a great talk. It's great to see this kind of progress on a tough problem. So I was just wondering about, is there similar progress or a way to extrapolate this for strength parameters? These are stiffness parameters, shear wave velocity and small strain modulus.
Yeah.
What about large strain modulus getting up to failure conditions? Is there any corollary, parallel work going on?
I mean, generally what happens right now is we measure the small strain moduli in situ. We measure the nonlinear moduli and strength parameters in the lab, and then we marry them together, right? We have done nonlinear in situ testing, where we push sensors into the ground, for example, and we use T-Rex, right, big shaker truck, and we develop large strains in situ. But man, the boundary conditions, we don't know what the boundary conditions are. Flow is happening in granular materials. So it's pretty hard. We're not super good at nonlinear in situ measurements yet. I think we'll get there in the future. But one of the very interesting things we're working on right now, I've talked with some people over the past few days, is we're using seismic measurements to measure, or I'll say estimate, void ratio in situ. In saturated soils, we can do that, but we have to make P-wave velocity measurements, which I didn't even talk about today. We have to make P-wave velocity measurements that are accurate within 1 to 2%. But if we do that, we can estimate void ratio of granular soils in situ, which is huge. The other interesting thing that we're studying right now is damping. So measuring damping or attenuation in situ, which is another really important property that up to now we've really only measured in the lab. Other questions?
All right, I guess we can stop there. Yeah, so
We have a reception outside, so if you have more questions for Professor Cox, you can talk to him, right?
Yeah, so reception outside, if you didn't hear that, go enjoy what you really came for. Yeah, it was my pleasure to be here, so thank you very much, and I hope that at least you caught something new. Appreciate it. Thank you.